Well, we have, so zeros, we have another name, actually a couple other names for that. We have x-intercepts, those are the two main ones you'll hear, especially in Algebra 2. We also sometimes call these roots, solutions. So, kind of some synonyms for zeros. Basically what we're looking for, this is a quadratic equation, and hopefully you kind of remember just a general sketch. The parent form of a quadratic looks like that. It's called a parabola. Everybody remember that from Algebra 1? Or maybe I've said it before, I think. So if it is moved around, it can cross the x-axis up to 2 times. So if it just comes down and bounces off, that's just once. Could also come from the bottom, bounce off, that's just once. Or it could be moved around such that it crosses twice. In any case, we're looking for those values, those x values, where y is 0, where the function is 0. Does that sound familiar? Okay, so that's why we call it zeros. Here, here, all these places, y equals 0. So when we look at this, we need to get that set equal to 0. And again, it's because it has the bx term. If we labeled terms, we would have the ax squared term is there. This is our bx term, and that's c for a, b, and c. Okay, so as soon as we see bx, we need to get this set equal to 0. And so we need to add 11a and add 6 to both sides. Can I combine those together? Like, can I say 3a squared plus 11a is like 14a squared? Is that okay? Well, they're not like terms. So you have to just leave them separate. Okay, both of these are gone. Those terms on the right. So now we have a 0 over there. Okay, so basically what we just did is take that and set it to where we are looking where it crosses the x-axis. Is it possible to have it not cross at all? Okay, I mean, like, could we have a parabola that's down here and never goes across the x-axis? What do you think? I mean, I just drew it. Is that okay? Yeah. So we can have that situation, but what happens when you do is that you end up with the imaginary number system to solve it. And so it's like your answer would be like square root of -4. Well, we can't square root a negative. That's those kind. Okay? So for geometry, we don't deal with imaginary numbers. You will either have it cross once or touch once or twice. So you're looking for that. Okay, so I see the bx term. There is a bx term. So what does that mean our tool will be? Yeah, so star. Star and star is factor. Remember up here we do a times c, b at the bottom, and a on the sides. What is a times c? Oh, before we do this, I forgot to mention, there isn't this, but what should we look for before we star? Hi.
Is Elizabeth here?
Well, there is an Elizabeth.
Elizabeth from Romero?
Yep.
Right, talk to Elizabeth for just a minute.
Sure, she's coming. She knew you were coming, so she was in the corner.
Okay.
What should we check for?
Two parties last week, and you read this.
GCF, right? Guys, if you don't have this written, write it. Don't forget to check for a GCF. Is there a GCF? Is there something that all three of those terms have in common? Nope. Can't divide all three of them by the same number or letter, right? So we don't have that. Okay, what's A times C? What's B? 11, and A is 3. A is out front. We need factors of 18 that add up to 11. Are there any such factors? Good job. Yeah, 9 and 2. Okay? So we have 9 times 2 equals 18. 9 plus 2 equals 11. So we're good there. Now we need to simplify. This one is good. Can't simplify. But this one still needs to be. What goes into both 3 and 9? 3. So this becomes 1 over 3 instead. We'll use those numbers. Okay, so we get x plus 3 times 3x plus 2 still equals 0. This is now factored form. Okay, how do we solve? Those are the factors, like just a different way of writing that equation. But how do we find out where those x values are, those zeros? What do we do from here? Well, before I do that, do you guys see two things? Let's say box times circle. Actually, that looks like a 0. Box times triangle equals 0. You see it as two things, right? Box, triangle. Two things being multiplied equals 0. The only way that can be true is if one of them is, right? Or perhaps both of them. So that's called the zero product property. If two things are multiplied and make 0, something is 0. That's what that says. So that means we have to figure out where this one is 0. Well, if I solve that little equation, I get x is negative 3. So if I plug negative 3 right here, what does this first parentheses become? If this now is negative 3, what's negative 3 plus 3? It's 0. What's 0 times this mess over here? 0, right? Who cares what it is? It's 0 when I multiply by 0. Okay, now do the same thing on this side. Where is this one equal to 0? Well, take your little steps to get that x by itself. How do you get rid of the 3? Hi. Okay, so look here. Same thing. If I plug negative 2/3 in for x, 3 times negative 2/3 is negative 2. So this would become negative 2. What's negative 2 plus 2? 0. 0 times this whole thing is still 0. Okay, so we have two places where this becomes 0. So thinking back to that parabola, it's over on this side because this one is at negative 3 and this one is at negative 2/3. So the parabola is on the left side of the y-axis. Okay. Now in geometry, we're not super concerned about this parabola on the coordinate grid. We're not worried about graphing or the details of the algebra behind it. But next year you'll study the heck out of this. So the more you can grab onto this next year, the easier that will be. Okay. All right. Well, how many of you got those two zeros? Anybody? Okay. So this is why we keep reviewing this. How close did you get? Okay. Where did it go wrong? Anybody willing to share?
Whenever I got to the checking, like we check if it's like 0 or whatever, I forgot to do that, so it's.
Oh, here at this part?
Yeah.
Okay. Did that ring a bell? Okay. Anybody else willing to share? Okay. It's a pretty, if something factors, this is a pretty consistent process. So GCF star, and then set each factor equal to 0 and solve. Alright. Good, that was a good review of that then. I'm glad we did it. I will continue to put these up all year long. So remember we started the polygons, mostly quadrilaterals is what we'll study, but this is polygons and quadrilaterals. And we defined polygon, two-dimensional closed shape with straight sides. And then we talked about types. We will only be studying convex, which means all the vertices are poking out, not in. And we'll study both regular and irregular polygons. Okay. Remember, regular was kind of the arch typical kind, like it's the perfect octagon stop sign shape, not a wonky looking one, etc. Irregular has different side lengths and angles. Okay, I asked you to know the names of these polygons up to a decagon just by name. So without looking, what is the name of a 7-sided figure? What was it? Heptagon or septagon? Good job. What was the name of a 3-sided figure? Triangle. Or a trigon, or we said it was good. How about a 9-sided figure? Nonagon. Good job, guys. Okay, our goal really was yesterday to get into the angle measure. So, how many degrees are in every one of those angles in a polygon? So we said the total interior is equal to 180 degrees per triangle times the number of triangles that we could draw, which was always 2 less than the number of sides because those first 2 vertices are always connected. And then we just had written this green formula, so that's where we'll pick up here in a second. But this is, actually, let's come to this in a second. So we put this one in our notes yesterday. So a polygon has a total measure of interior angles, which is 1800. How many sides? So remember that we had to write the formula first. And then plug in what we knew, which in this case is the left side, and then solve for n. Sometimes I'll tell you n and you solve for the left side. Sometimes I'll tell you the left side and you solve for n. Okay? And then we said, hey, you could do it this way, which is pretty slick. And we got n was 12-sided figure. Were there any questions on that example? Or the 2 ways that you can do it? Okay. So that kind of both of those are, they're the 2 versions of how to use this in the most basic sense. If this is a regular polygon, so now it would be a regular dodecagon, since it has 12 sides. If it was regular, we just started talking about how would we know the measure of each angle. What did we say we would do? There's 1800 degrees in the whole thing. How many angles are in it?
12.
There are 12 angles because there are 12 sides. It's the same. So how would you determine, and I'm not going to try to draw the whole thing, but let's say it's like that. Okay? So how many degrees are in that one angle right there? How would you determine that? If you know there are 1800 in the whole thing. Let's kind of make this more relevant to us. If I told you we had $1,800 in our pockets in here, and everybody had the same amount, that's the same concept, how would you figure out how much each of us have? Just multiply? Or would you multiply? Okay, but that assumes we know how much we all have. So let's say there's 10 people. There's 3, 6, 9. So we just need one more. $1,800 split by 10 people. What would you do?
Divide.
It's divide, right? It's just like, I mean, wouldn't that be nice if I was holding $1,800 and said, hey, come get your share, what would I be doing? Dividing it, right? That's the same idea. if we have 1800 degrees, that is not a very pretty thing. In fact, I'm not going to use it because it was ugly, too ugly. Okay, if I have some number of degrees to split up between all of these things, all of these different angles, that's called division, right? Okay. In our example that we're talking about, it's 1800 degrees. This is not a dodecagon. What is it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What's it called?
The decagon.
So it's a decagon. So we have to take 360 degrees off of that, which is 1440. Okay, so this one, 1440 degrees getting split up between all those angles, right? So what do? Just divide by 10, right? In this case, 10. So each angle has how many? 144 degrees, right? Where am I losing you? Are we all good? Can you give me a thumb? Take the total, divide it by how many there are. That's literally all we did right then, right? Are we good on that? Okay. You know, if you have 3 brothers and sisters in your family and your parents split up something they're giving you, they just divide it equally between the 4 of you, right? That's all we did. 1440 degrees in a decagon split up by 10 angles gives us 144 degrees each. So, in our notes, we started by writing that equation down. And all it says was take the total and divide it by how many angles there are. This formula has 2 sides, just like the other one. So the reason I had you write this blue note is because I sometimes will tell you each interior angle is 144 degrees. How many sides is there? It'll work both ways. So let's kind of get into some examples of this. So what is each interior angle of a regular 17-gon? Shall we just do this one in your notes? I'd like to do 2 versions because this is like what I would consider the straightforward version where you're just plugging it in. So let's squeeze 2 examples in here. Please underline the word each. So what is the measure of each interior angle of a regular 17-gon? How many sides does a 17-gon have?
17.
Yeah. This is a weird name. How many angles does a 17-gon have? 17. Well, because you were thinking how many triangles can you draw in a 17-gon? Which would be 15 triangles, but there are 17 angles in it. How come that's open? Your computer. Do you need it right now? Okay. I only underlined one of the key words in here. What's the other key word?
Regular.
Yes, each is one of the key words. The other is regular. It has to be regular, otherwise we can't divide. Think about back to my example. If your parents are giving you you and your siblings something, but you get more of it, is it evenly divided? No, that's the idea of irregular. Okay, so it has to be regular for this to work. I'm going to say it this way, sorry, if you already started writing that. Say, make sure you know it's regular first. Alright, if so, then you're going to start with the formula, right? Which says each interior equals 180 times n minus 2 divided by n. How many degrees are in a 17 gone? Like how much money is there to go around, right? That's the top of this equation. We need to know the total degrees that we have to spread around first. Oops, it's already a 2. You'll see a common theme here. Plug in what you know. What do we know? Do we know each interior angle? No? That's what we're trying to find. What do we know in this equation? I'm saying, what do we know that we can plug into it? Yeah. We know n. Okay? So plugging in each interior equals 180 times 17 minus 2 divided by 17. So plugging it in, that's what we know. And from there, it's just to solve, right? Like, it's actually just a calculator exercise. The next example will be more work for this step. So, solve for the variable. In this case, the variable is the each interior angle. Well, this is 180 times 15 divided by 17. So I don't know what that is. Let's go do it. 180 times 15, that says 18, divided by 17. Okay, actually before we punch that in, alright, what is the 180 times 15 telling us? The top, the numerator?
That was 15 triangles into the shape.
Yep, we're putting 15 triangles in that 17 gone, and what is the 180?
How many degrees are in the triangle?
Yes. So this is the total degrees that we're spreading out, right? The 180 times 15 is the total degrees. Let's actually name that on here. Total degrees over number of angles. So how much money do we have? We have $2,700. 2,700 degrees, right? Splitting that, or dividing by 17. gives us that 158.82 degrees per angle. These will not always be whole numbers at all. Okay? Very rarely will it be a whole number. So we have 158.82 degrees per angle. Obtuse or acute? Quite obtuse, right? Like we're starting to get closer to 180. It's almost like a flat line. Okay, so basically you're just solving for the total and dividing it up. That's really the way this equation works. Solve for the total and divide it up. This one is the other type of example. So look here and read it with me. Each angle is given. Each angle, there's our keyword, regular, measures, and it gives us the angle. How many sides does the n-gon have? Okay? So if you notice here, what is the measure of each? This example says each is how many sides? So this time we're going to solve for n. Do you see the difference? And by the way, this is the figure that we're solving for. What does it look like?
Circle.
Okay, it's not a circle, but it looks darn close to one. So let's go. I'll have you write this down. And so example 2, each angle, we need to say interior, because here in just a little bit we'll do exterior. Each interior angle of a what word? Regular polygon is 172.8 degrees. How many sides are there? Really, we're asking how many angles there are, but that's an okay way to say it. Okay, get a second to write that down. Yeah, so steps are the same. That means we need to make sure that it's regular first. So do we know that? We were told that it is. Okay, step 2. Write the each interior formula, which says each, and I like to abbreviate each interior, because 180 times n minus 2 over n. What do we know this time? So step 3, plug in what you know. What do we know this time?
Each interior.
Yeah, we know each interior, right? So this becomes 172.8. And the whole right side stays the way it is because we don't know n. Everybody following? We are done at this point with the geometry. It's just algebra. So how are your algebra skills with solving for a fraction like that? How do you get n? So 2 things have to happen. We have to get n together, because it's in 2 places, and get it by itself, so that we can say n equals the side length. How do you suppose we do that? While you're thinking, I'm going to put a 3 for step 3 right here. I also forgot to do it over there. Step 3. 2. Step 4. Step 3. Did you brush up? Well, we learned early on in this year how to get rid of a fraction, which was what? Multiplied by the denominator. Yeah, great. So this is going to be n times, and I'm going to try to do some color stuff here. Okay, so we're going to multiply both sides by n. This, by the way, is going to be the same every time. Both sides by good old n. Why is it going to be the same every time?
Sorry for this interruption, but Mr. Pism, please call the main office 22100. Mr. Pism, please call me 22100.
Why will that step be the same every time? For this kind of problem. When we're solving for the side lengths, we will always multiply by n first. Why? Yeah, essentially. I mean, isn't this side going to be the same every single time? The only thing that will change for this problem is the green part. Right? Like in one that we just looked at a minute ago, this was 144. If I told you this number, it would be 158.82, and I would ask you for the sides. But the right side will always be the same thing. So to get rid of that n will always be the same process. Just multiply by n. What happens to these two n's? They're going to cancel. Right? So now we have, just without a fraction, we have just a regular linear equation. So let's take a break and we'll pick up. Alright, so we're going to cancel these n's on the right. Over here, we still have the n times 172.8. That doesn't change. But you can put it behind the number like we're used to seeing. Right, we don't leave it out front. Okay, so now it's just down to a normal equation. You guys have solved these kind 150,000 times. So what do we do from here? We want to get n's together and then get them by themselves, or get it by itself. Subtract what? Well, the only n I can subtract is this one. And that would create a situation where it's equal to 0. I probably don't want to do that. Yeah. What's 180 times 2? Well, times negative 2. Yeah. Okay. Guys, on the right side of this, will it ever look any different than this? Have we done anything to the right side that is unique to this problem? No? I mean, here's what I mean. Don't do this to your notes, but just take a second to look. The only thing I plugged into this problem is the green 172.8. That's it. Which means all of this stuff is what we substituted. Like, that's what changes. Do you see how this will always be the same? Right? So that's good. All of that is kind of nice. Okay? Solving from here, what do? We want to get these n's together. So it's kind of concerning if you're a boss right now. Just saying.
I just can't really see it.
How do we get those two together?
Try 180.
Yeah. Is it okay that we're gonna have this negative n value? Let's go ahead and punch it in. 172.8 minus 180 is negative 7.2. Is that okay? Can we have a negative number of sides? That would be weird, wouldn't it? Are we going to have a negative number of sides? Why not? Like, what's our next step going to be? Divide a negative by a negative, which gives a positive. Okay? So this 360 will always be negative. So if this is not, you're going to end up with a negative side length. And that doesn't make any sense. So, yes, that should be a negative number right there. Divide by negative 7.2. Get n. And I don't know what that is either, so let's go do it. 360, and I should make that negative. Negative 360 divided by this guy gives us 50 sides. Can that be a decimal? Like over here we said the angles will often be a decimal. Can this be a decimal? What is n? What does n mean? Number of sides. Can we have 14.2 sides? No way. That doesn't make any sense at all, right? How would you even draw a 14.2 sided figure? That would be like saying that part of it's not done, which means then it's not closed figure, so it's not a polygon, right? So this is a 50-sided figure. And I don't know if you saw this, but the name of that is a pentacontagon. So you know how you were saying yesterday there's really not a pattern? You can kind of see one with pent, right? That's like pentagon. That kind of thinks of, or reminds us of 5. But pentacontagon is a 50-sided polygon. And it looks pretty much like a circle. So, I don't know how many more sides we would need to get before it looked exactly like a circle, but it would be a few. Questions on that side of the examples, that version? Which one's easier?
Definitely the first one.
I would say definitely the first one, because all you're doing is sticking a number in for n and multiply, divide. Here you got to do some algebra to solve. But I did tell you, and we could write this down, that the right side of this will always be the same. So what's going to change? Like, where do we start? Well, so here, this stuff would be different, right? This negative 7.2n is where you're going to see a difference. The other side will always end up saying negative 360. It will. I guess if you want, I hate to do this because then students just don't think, but I'll give you this. I should probably put that arrow. Oops. Should put that arrow right there. Okay. that line will always be whatever each angle is, n minus 180 n. It will always be the simplified version of that equals negative 360. Because the right side doesn't change, the left side only does in the sense that we add an angle measure in there. Okay? You guys, what shape is the sign? Yeah. 1, 2, 3, 4, 5. Pentagon. How many sides does it have?
5.
Is it regular? You'll never look at this sign the same again. Next time you see one, you'll probably run over the people because they'll be like, what the heck was that again? Also, it's usually yellow, right? Anyway, is it regular is the question. Don't overthink it.
No.
Do all the angles look the same?
No.
No. Like this one is acute. These are more like 90, right? Plus it says it has 3 right angles, but no, it's definitely not regular. So can we do this process on this sign
No.
that we just wrote?
No.
No. Okay. So it says it has 3 right angles and the other 2 angles are congruent. So it would be 90, 90, 90, congruent, congruent. How would you figure that out? Since we can't use the method we just did because it's not regular. Give it a shot. I want you to think through this. Remember that this whole process is using the total degrees in the figure, no matter which way you do it. Time to work on that sheet. So. All right. First, we need to look at our equations. Unless you have it memorized, that would be awesome. So which of these might we need? Or maybe we need both, but which of the ones for sure do we need? The total. And the reason why is because this one requires it to be regular. And it's not. Like this says must be regular. Not regular. So we can't use that second one. Okay? So we're using this first one. Total interior equals, and then we have this 180 times n minus 2. Okay? And I think probably, maybe all of you, but some of you will eventually have some of these memorized. So this is a 5-sided, a pentagon. Anybody have that memorized yet? How many degrees are in it, I mean? Okay. So if you don't, then you do have to do the right side. So this is 180 times 5 minus 2, which is 540. And you'll see a pentagon probably enough that you'll start to memorize that. Okay, this other side, I need to leave the way it is and fill out what I know. I do know that I have 3 90s. So start putting that on there. And then I have 2 congruent angles. What should we call them? What should we call these 2 that we don't know? Like we don't know them. What do we usually call things like that? We call them x, right? And they're the same, so call them both x. Okay? Everybody clear on where that all came from? Now I got my line kind of crooked there, but in other words, the total interior angle is the total of the 5 angles that we have in it, right? So we get 270 plus 2x equals 540. How do we solve from there? Yep, and then divide by 2. So we get 135 degrees each. Okay? What was different about that than what we just wrote in our notes as examples? Okay, it was not regular. So looking at the two that we wrote here, it's definitely not the right side, because it had to be regular. It was this version, but instead of just writing each, sorry, it wasn't actually that. It was not either of those specifically. It used this total formula on the right, but on the left side, it was just adding the angles up, I guess we'll just say it that way. Okay? So you're going to see these kind of look pretty nasty sometimes, but they're really not. Let me show you what I mean. We'll come back to that. So look at those two. If I handed you that 20 minutes ago, it would look like, oh my gosh, what do we have to do, right? It shouldn't look that way now. Tell me why. What do you think we would do? Let's just do the left one. We only have two equations that deal with interior angles, right? We only ever will have two equations that deal with interior angles for this. So is this each or is this total? That's really the only thing you have to decide. Well, but it's not because it's not regular, right? Does everybody see that it's not a regular polygon? I mean, the biggest clue is this side congruent to that side? Not even close, right? So it's not regular. Can you use equation 2? The second one that we put in the notes. No. Because to use it, it has to be regular. So it really narrows it down to one equation, right? Okay? So which is that? What is it? What is the one equation? Say it again.
Total interior.
Yeah, total interior equals 180 times n minus 2. Now, how in the world do we use that simple looking equation with all these x's? You said something. What was it? Did you say something? Okay. Well, look here, please, everybody. Do you see how this is basically two different names for the same thing? The total or the total, right? So this one is giving me the total based on side lengths. This one is giving me the total based on all these expressions. Kind of like we did with the people sign. Okay? So let's fill this side out. Hopefully you can see that this is going to require some room. So I'll move it over a little. 180, what is n in this case?
8.
1, 2, 3, 4, 5, 6, 7, 8. Is that a regular octagon? Definitely not, right? Okay, so that's going to tell us the total degrees in that thing. Is it going to be different if it's regular or not regular? Nope, it makes no difference. Okay. That is going to tell us the total degrees. This left side is how we get them. How do we get all those total degrees? Well, do you guys see that we have 4 of these? 1, 2, 3, 4. And 4 of these. Do you agree that the two green things also tell us the total? Except for it's not going to tell us a number, right? We have to solve for that. But it's an equivalent expression to this. So an octagon, I told you you'd memorize this eventually. An octagon has 1,080 degrees, made up of all these pieces. So it's saying the same thing twice with just two different components. That's the total degree side. This is the how you make them up side based on the different angles. Okay? Why don't you guys try that one? The one on the right.
We can do it outside.
Alright. How many sides is this? Well, first of all, is it regular?
No.
Not even close. Which tells us that this cannot be an each interior angle formula, the second one we wrote, because it's not regular. We know that these are interior angles because they're inside, so we're going to be using this equation. There are 6 sides. And again, you'll have some of these memorized, hopefully. So 180 times 4, right? 6 minus 2 is 4, so 720. Guys, what that tells us is in here, all those angles make 720 degrees, right? It tells us the total degrees in that hexagon is 720 degrees. And how are we getting those 720 degrees? We're just adding all of these up, right? That's all. The total has to be each angle added up. So you could write it out. That's fine. That's like angle, 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 angle. Kind of got off there, but 1, 2, 3, 4, 5, 6 angles, right? That's all we're doing. We're saying, hey, these 6 angles have to add up to 720 degrees. Okay, that is the same as doing the fact that we have 4 of the 3x plus 20s and 2 of the 4x. Those are equivalent statements. So whichever one you like is fine with me. How do we solve this? Distribute 12x minus 80 plus 8x equals 720. Combine your like terms, so you get 20x minus 80 equals 720. Add your 80 over to start getting that x by itself. $20x equals 800. And then divide to get 40. So x is 40, not the measure of any of those angles, right? Huh? Okay. How'd that go for you? Alright. How about something like this? How would you do this one? This is more like that sheet I just handed you. How would you do this one? Total interior, right? 105 plus 1, whatever that says. I'm going to call it 115. Plus 75 plus 130 plus x. And then what shape is that? Pentagon. Okay, so pentagon is 540. If you don't know that yet, then do n minus 180 times n minus 2, and you'll get 540. Okay? That's all. Everybody kind of follow what we're doing now? Okay? So, on your sheet, today we are ready to do, we haven't done exterior angles, so look at number 3. You see how those are exterior to the polygon? They're outside. Those kind we'll do tomorrow. Same with numbers 5 and 6, etc. So we're not going to do this. So today, circle 1, 2, 4. 1, 2, 4, 7, 8, 9, 10. We can do all those. And I think we'll stop there. And we'll pick up with the next one. So we have 10 minutes. I'd like you to work till we're done on those ones. Actually, do we have 10? Yes, we have 10. 10 minutes. So 1, 2, 4, 7, 8, 9, 10.